Alright, so I'm just going to do another video, and it's going over just a very, very simple Lagrangian question. This is example 1.11 in the book Conquering the Physics GRE. So I'm just going to go through the example before I actually go through the additional problems. So what we're going to do here is the question wants us to find well, it doesn't really have a question, I suppose, but we're going to find the kinetic energy. And we're going to use principles that from the Lagrangian to get there. So to begin with, we want to describe the position. That's our first step. The position of the object we're interested in, which is this mass. So we have this pivot, this little pendulum about the pivot, and hopefully you can see that it's, let's set the origin to be when theta is equal to 0. So hopefully you can see that for the x component, it'll be just L sine theta. And then for the y, L cosine theta. Just using the triangle. Try to write that sideways, sorry, it looks ugly. So we find that, I'll do it in black, x equals L sine theta. And y equals L cosine theta. So after you get the position, we're going to find the velocity, which velocity is just the derivative of position. So all we have to do is take its derivative. So the derivative with respect to time, well, the derivative of sine is going to be cosine. So you get L cosine theta. But remember, this dot, x dot, is dx by dt. So we're taking the derivative with respect to time of L cosine theta. So we have to do this actually implicitly. So what that means is we have to multiply by theta dot. We have to do a chain rule essentially. And we have to do the same thing for y. So y dot, let's see, we want to take the derivative of, I'm sorry, this should be a negative L cosine theta because it's below, right? If we let this pivot be our xy. So that's going to make a difference because when we take the derivative, negative sine theta, obviously the derivative of cosine is negative sine, so you end up just getting positive L sine theta. And then for the same reasons as before, theta dot. So hopefully it makes sense why we're doing the chain rule here. Now, from here, we can get the kinetic energy. Because the kinetic energy is equal to 1/2 mv squared, or 1/2 m x dot squared plus y dot squared, right? Because for our velocity, you have v, but you have the x component, you have the y component. So v is the square root of vx squared plus vy squared. So then v squared is just the square of our components added together. So just another way of looking at it, obviously looks a little different than physics 1, but it's the same idea. But notice that we know what x dot, we know what y dot is, right? We already found those. So we can plug those in, and you get that your kinetic energy is 1/2 the mass L dot squared, so that'll be L squared theta dot squared cosine squared theta plus L squared theta dot squared sine squared theta. That's our y dot. So we can say then our kinetic energy is 1/2 m. I'm going to factor out in L squared. I'm going to factor out a theta dot squared, and you're left with just cosine squared theta plus sine squared theta, and that's obviously Pythagorean's identity. This is just 1. So we find that your kinetic energy is 1/2 ml squared theta dot squared. Now, that is equivalent. That's the exact same expression for our rotational kinetic energy, which says, so kinetic energy rotation is 1/2 I omega squared. Now, I is our moment of inertia, which if you remember for point mass is just mr squared, which in this case we could say is just ml squared, right? So this I is equal to ml squared, so that's this part. And then just remember, this is your angular velocity, and this is your position. So the derivative of your position is your angular velocity. So angular velocity squared is equal to theta dot squared. Those are the exact same things, okay? Because theta is just a position. So those are the same things. And that was really the gist of the problem. Just kind of getting you familiar, I guess. I figured it'd be worth doing, especially if you've never seen it before, the Lagrangian. But yeah, just an example out of the book. I figured it'd be worth doing and didn't take too long.